Welcome all of you for this session on the properties of ideal gases. So the gas is an important classification of fluid. Fluid can be broadly classified into liquid and gas. A fluid is the one which is about to flow and the application of external force. The important property of the liquid is density, whereas the important properties of the gas are pressure, volume and temperature. Today we are going to say about the ideal gas, and hence the important properties are pressure, volume and temperature. To study about these properties, out of these three, we have to maintain one as constant and study the influence of one parameter over the other. So initially let us keep the temperature equal to constant. So what will be the effect of pressure on volume? As we know, the pressure is inversely proportional to volume at a constant temperature for a gas as given by Boyle's law. Similarly, at a constant volume, the pressure will be directly proportional to the temperature. So we are going to combine these two laws. Then I will end up with PV is directly proportional to T. So we are going to combine one and going to combine two. Then PV will be directly proportional to T. If you want to remove this proportionality constant, I have to introduce a constant. So it will be equal to R into T, where this R is called as characteristic gas constant, which means this R value will be varying for each and every gas. That is, R of oxygen will have definite value, R of nitrogen will have definite value, R of air will be definite value. So it's not going to be constant, it will be varying with respect to the gas. And hence it's a gas of a particular gas, and hence it is called as characteristic gas constant. And this equation has been given for unit mass. If it is for m mass, then the equation becomes PV equal to mRT. So PV equal to mRT, where m is the mass of the gas. This equation is called as ideal gas equation, which is derived of the concept of Boyle's law and Charles' law applicable to a ideal gas. We also know that the number of moles, small n, is given by mass divided by molecular weight. This molecular weight can be either integrated as m dot w or by a symbol called mu. So generally we used to define as n equal to small m by mu, where n is the number of moles and m is the mass and mu is the molecular weight for a particular gas. Let us come to this ideal gas equation, PV equal to mRT. I want to find the unit of R, so keep R along one direction. I will end up with PV by MT. So PV is nothing but product of pressure and volume centimeter octane. The unit of any octane will be joules, by mass is kilogram, and T is Kelvin. A very important point is that this K should be in small letter, J should be in small letter, and capital J and this K R should be in capital letters, which means these are the name of the scientists, and hence we are indicating by the capital letters. Like Kelvin is the name of the scientist, Joule is the name of the scientist. So R will be equal to, the unit of R will be Joule divided by kilogram Kelvin. Now, I will give this equation number as 3, this is equation number as 4. Equation number 3 and 4. Substituting 4 in 3, we get. So it will be PV equal to N into mu into R into T, because M will be equal to N into U from 4. So substitute for M in this equation. I will end up with N into mu into R into T, where mu is nothing but called the molecular weight of the particular gas. So this PV can be written as N R bar T, where R bar is nothing but universal gas constant. Universal gas constant. Which means this value will not vary for each and every gas. It will be same for all the gas. If I am going to take R of oxygen, it will be same. R of nitrogen, it will be same. R of carbon dioxide, it will be same. R bar. So we can see that the universal gas constant is called universal because this value will not change for each and every gas, and hence it is called universal gas constant. And where R is given by mu into R. So we can see here, I replace mu R with R bar. So this R bar is nothing but the universal gas constant, and the R is nothing but the gas constant, and mu is the molecular weight. So R bar will be given as mu into R. And most of the classes, when I asked the students what is the unit of N, they used to tell the unit of N is no unit is a constant, it is a number of moles. But it's not right. But it's not right. So we can compare 3 and 4. Both are nothing but ideal gas equation. If this equation 3 is in the form of mass basis, and this is 4 is in case of molar basis. Okay, PV equal to N or T. Let us have the unit of N, so that it will be useful. It's also similar to the mass, but it's nothing but molar mass. So the unit of N is, what is the unit of mass? Kilogram. So similarly, what is the unit of N? It should be kilogram of mole. Kilogram mole. So don't feel or don't think in your mind that N is number of moles and is a number. It is not like that. N is representing the molar mass, and hence N is having a unit of kilogram mole. Now let us derive the unit of R bar, which is nothing but the universal gas constant. So from this equation 4, R bar will be equal to PV by NT. So P into B is nothing but octane. The unit of octane is nothing but energy, or the unit of octane is nothing but joules, which is also similar to the unit of energy. So it is joules. The unit of N is kilogram mole, and that of temperature is Kelvin. So the unit of R bar is joule divided by kilogram mole Kelvin. Whereas the unit of R is joule per kilogram Kelvin. So this is based on mass basis. This is based on molar basis. Okay. So this is the unit of this R bar. Now let us go with Avogadro's law. Avogadro's law. What this law says is that a gram mole of any substance will have a mass numerically equal to its molecular weight. To its molecular weight. So it's a very important statement. A gram mole of any substance will have a mass numerically equal to its molecular weight. Now before going to know about the mass, let us know what is the molecular weight of every gas constant. So let us see about this periodic table: hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Here the rest will be sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Okay, let us have the first 18 elements. So these elements are arranged according to the increasing atomic number. So it's having atomic number of 1, 2, 3, 4, 5. Carbon is atomic number 6, nitrogen 7, oxygen 8, fluorine 9, neon is 10, sodium is 11, magnesium is 12, aluminum 13, silicon 14, phosphorus 15, sulfur is 16, chlorine is 17, and argon is 18. Now the next step is the molecular weight. So this is called as the Mendeleev table, periodic table, based on the increasing atomic number. And hence, if you want to see about its molecular weight, for hydrogen alone it will be 1, whereas for the other elements it will be nearly twice of those atomic number. It is 4, it is 6, it is 8, it is 10, it is 12, it is 14, it is 16, it is 18, 20, and sodium is 22, magnesium 24, aluminum is 26, silicon is 28, phosphorus is 30, 32, 34, 36. So we can see that the molecular weight of the elements are nearly twice as that of its atomic number, except for hydrogen. And this value will be slightly varied. When you are going for higher order elements, it will even go to some 45.1. Slightly there will be variation, but almost it will be twice of the atomic number. So you should know the molecular weight before we are going for this concept. Okay, I hope now I can erase this molecular weight of the elements. Now let us find the molecular weight of methane. The chemical formula for methane is CH4. So we are having 4 hydrogen atoms. Into its molecular weight is 1, so it is 4. We have 1 carbon atom. Into its molecular weight is, you can see here, is 12. So it is 12. Is 16. So we can see that the molecular weight of methane is 16. Okay. Similarly, let's take another example. Let's take carbon dioxide. I want to find the molecular weight of carbon dioxide. So it is 2 molecules into the molecular weight of oxygen is 16. So it is 16. 2 is 16 will be 2. Carbon it is 1 and its molecular weight is 12. So it is 12, and hence the molecular weight of carbon dioxide is 44. The molecular weight of carbon dioxide is 44. Similarly, we can derive for any gaseous constituents. Okay, fine. For nitrogen, it is 2 into what is nitrogen? 14. So the molecular weight of nitrogen molecule is 28 because nitrogen is a diatomic molecule. Okay. Now we have a good idea about the molecular weight. Now let us proceed to this statement. What does this statement say? 1 gram mole or 8 gram mole of any substance will have a mass numerically equal to its molecular weight, which means 1 gram mole of oxygen will have 32 gram of mass. 1 gram mole of oxygen will have a mass numerically equal to its molecular weight. We know that the molecular weight of oxygen is 32 because there is a diatomic. Similarly, 1 gram mole of nitrogen will be equal to 28 grams of nitrogen because the molecular weight of nitrogen just we saw is 28 grams. Similarly, 1 gram mole of methane will have a mass of 16 gram. Just now we derived 16 gram. Similarly, 1 gram mole of carbon dioxide will have 44 grams of mass. 44 grams of mass. Instead of taking 1 gram mole, if I want to take 1 kilogram mole, then instead of 32 gram, I will end up with the 32 kilogram. That's it. So, if I want to take 1 gram mole, the mass will be 32 grams. Instead of that, if I want to take 1 kilogram mole of oxygen, the mass will also be in kilogram kg. So, here also it is 1 kilogram mole of nitrogen will have 28 kilogram of mass. Similarly, this 1 kilogram mole of methane will have 16 kilogram. Please recall, this is not capital K, this is only small k. Similarly, 1 kilogram mole of carbon dioxide will have 44 kg of mass. So this is the statement which is very important for deriving this Avogadro's law. So 1 gram mole of any substance will have a mass numerically equal to its molecular weight. I hope now you may got the physical understanding of this statement. Now let us proceed to the further one, the real statement of the Avogadro's law. Let me take, I have 3 different beakers. Now I am going to put oxygen, here I am going to put nitrogen, here I am going to put air, nothing wrong. Now all this oxygen, nitrogen and air are they going to be at 1.013 into 10 power 5 Newton per meter square or 100% pressure. And they are going to maintain at a temperature say T equal to small t equal to 0 degrees Celsius or capital T equal to 273.15 Kelvin. So I have taken oxygen, nitrogen and air. What the condition means? I am going to take only 1 gram mole of oxygen. Similarly, 1 gram mole of nitrogen, 1 gram mole of air. At what condition? At a condition of 1 atmospheric pressure, which is nothing but 1.03 into 10 power 5 Newton per meter square or Pascal, and the temperature is 0 degrees Celsius. The C should be capital because the name of the scientist. And the temperature is Kelvin scale is given by RA 273.15 Kelvin. Now, under these conditions, the 1 gram mole of any substance here refers to the gaseous substance, will occupy a volume equal to 22.4 liters. Will occupy a volume say 22.4 liters. So the volume occupied by oxygen must be equal to what? 22.4 liters only. Even though its molecular weight may be different, 32 gram. Here the molecular weight can be 28. For air it may be different. But the volume occupied by all the 3 substances differently, they will also occupy a volume say 22.4 liters. This is nothing but called as Avogadro's law. The Avogadro's law states that a gram mole of any substance at normal temperature and pressure say 1 atmospheric pressure and 0 degrees Celsius will occupy a volume of 22.4 liters. Will occupy a volume of 22.4 liters. I hope you can understand. Let us move further. So what is 1 liter? What is 1 liter? So if I am going to have a beaker such a way that this breadth dimension is 10 centimeter, this height is also 10 centimeter and the width, this dimension is also 10 centimeter. That is the thickness along the diagonal perpendicular to the board is also 10 centimeter. Now, the volume which can be occupied by this particular beaker is called as 1 liter. So 1 liter will be equal to 10 into 10 power into 10 into 10 centimeter cube. 10 into 10 into 10 centimeter cube. So 1 liter is equal to 1000 centimeter cube. That's what I want to tell you. 1 liter will be equal to 1000 centimeter cube. Now I put 1 gram mole of any substance, maybe oxygen, hydrogen, any substance will occupy a volume of 22.4 liters. Okay. So 1 gram mole of any substance will occupy 22.4 liters. 1 liter will be equal to what? 10 power 3 centimeter cube. I hope you can understand. Otherwise, it's 22.4 liters. But we know 1 liter equal to 10 power 3 centimeter cube. So I can replace this with 10 power 3 centimeter cube. So, instead of 1 gram mole, if I am going to take 1 kilogram mole, it is not wrong. Instead of taking 1 gram mole of oxygen, I am going to take 1 kilogram mole of any substance. So, what is the volume? Multiply both sides by 1000. Here also I multiply by 1000 because to convert the gram mole into kilogram mole, there also I multiply by 1000. So, it becomes 22.4 into 10 power 6 centimeter cube. We also know that 1 meter cube is equal to 10 power 6 centimeter cube. 1 meter cube is equal to 10 power 6 centimeter cube. And hence 1 kilogram mole of any substance will occupy a volume of 22.4 meter cube. At what condition? At 1.013 into 10 power 5 Pascal and 0 degrees Celsius. Under this condition, 1 kilogram mole of any substance will occupy a volume equal to 22.4 meter cube. With this law, let us find out what is the value of R bar. Let us try to find what is the value of R bar. What is the ideal gas equation in terms of molar basis? PV equal to N R bar T. PV equal to what? N R bar T. Where now how much should be the value of N? N should be equal to 1 kilogram mole. Because that is the condition. N should be equal to what? 1 kilogram mole. So what will be the volume? Volume will be equal to what? 22.4 meter cube. This volume will become what? 22.4 meter cube. What about the pressure? The pressure is defined already. It should be 1 atmospheric pressure. So it is 1.013 in 10 power 5 Newton per meter square. And what about the temperature? Temperature is 0 degree plus 273.15, which is equal to 273.15 Kelvin. So now we have the values of N, B, P and T. So the only unknown is R bar. From this we can easily find out what is the value of R bar. So R bar will be equal to PV by NT. So P is 1.013 into 10 power 5 into volume is 22.4 by N is 1 because we are considered as 1 kilogram mole. In temperature is 0 degrees Celsius or is 273.15 Kelvin. So what is the answer?
8,307.
8,307.23. 307.23. So the unit will be Joule per kilogram mole Kelvin. This case should be small k. And if we are going to take exactly the values, instead of 1.013, we can even take the exact value like 1.01325. Then we will end up with the values 8314 some decimal. So the actual value will become 8.314 kilojoule because I converted the joule into kilojoule by divided by 1000 divided by kilogram mole Kelvin. So we are able to find the value of the universal gas constant by applying the Avogadro's law. Now you can feel the importance of the Avogadro's law, which states that a gram mole of any substance at a standard or at a normal temperature pressure of 1 atmospheric pressure and 0 degrees Celsius will occupy a volume of 22.4 liters. Based on that, we find out the value of R bar, which is nothing but universal gas constant. So what is the value of R bar of nitrogen? R bar of nitrogen 8.314. R bar of oxygen same value. R of carbon dioxide same value. And hence this value is not changing with respect to each and every gas. It is going to be universal. And again this gas constant is called as universal gas constant. The unit is very important. The unit is kilojoule per kilogram mole Kelvin. Okay. And we already know that there is a relationship between R bar and R. It is nothing but what? R bar equal to mu into R. Where R is the gas constant and mu is the molecular weight of the gas considered. Now, I know that R value is going to be constant. Now I want to find, for example, R of oxygen. That is gas constant of oxygen. Then what is the value? The same formula can be written as R bar will be equal to mu of oxygen into R of oxygen. Now I want R of oxygen, which is nothing but R bar by mu of oxygen. So what is R bar? R bar is 8.314 divided by what is mu of oxygen? Mu of oxygen is 32, because we know that mu is nothing but molecular weight. The molecular weight of oxygen is 32. So what is the answer?
0.259.
0.259. What is the unit? What is the unit? The unit is kilojoules divided by kilogram Kelvin. There should not be moles should be coming. It should only R. It is not R bar. So we can see that R of oxygen is given by 0.259 kilojoule divided by kilogram Kelvin. Similarly, we can find the value of R of nitrogen. Mu of nitrogen into R of nitrogen. So R of nitrogen will be equal to R bar by mu of nitrogen. So R bar is nothing but what? Once again 8.314. By nitrogen is what? Molecular weight is 28.
0.296.
0.296. The unit is kilojoule by kilogram Kelvin. So this is nothing but R of nitrogen. Similarly, you can find the R of air also. The molecular weight of air will be 28.96. So I can tell R of air will be equal to R bar by mu of air. So R bar is 8.314 divided by mu of air is nothing but 28.96. So what is the answer?
0.287.
0.287 is a kilojoule per kilogram Kelvin. So we can derive R of methane, R of carbon dioxide for any gas we can derive. So now I hope you know what is meant by ideal gas equation in terms of mass basis, in terms of molar basis. You know the difference between R and R bar, that is the gas constant and universal gas constant, and you know the relationship between them. And we also know what is the advantage of the Avogadro's law. From the Avogadro's law only we derive the value of R bar. So we move to the next step. Yes, we will move to the next step. Before going to the properties of ideal gases or mixtures, let us derive the entropy change happening during a process. Okay. So what is first law of thermodynamics? Q will be equal to W plus delta U. The first law of thermodynamics operated by a closed system says Q will be equal to W plus delta U. It is going to be open system. Q will be equal to W plus delta E. Now what is Q? It is TDS. Integral of TDS. So we already know that the area under the TS diagram, if it is an area, say it is a process from 1 to 2, this area under this TS diagram indicates the heat transfer. Indicates the heat transfer is a path function. Similarly, the area under the PV, the area under the PV diagram indicates what? The area under the PV diagram indicates what? The work done. The area under the PV diagram indicates you the work done. So from this diagram, you can find this is nothing but what? W1 to 2. And here T and P are called intrinsic properties which are independent of the mass, and S and B, where S is the entropy and V is the volume, they are called the essential property which are dependent on the mass. And we can tell this Q, then will be called what? Integral of T into ds. Similarly, this W will be called as integral of P dV and delta U. So I have not done anything. Just I know already. The area under the TS diagram is nothing but the heat transfer. The area under the PV diagram is nothing but the work transfer. So I applied those things to this equation of first law of thermodynamics. I want to differentiate now this entire equation. When I go to differentiate, what will happen? This integral sign will go away. This PdV will become simply PdV. As this delta U is a number, now it becomes a differential operator. It is not delta U, it is du. So there is a difference between delta U and du. Delta U is nothing but U2 minus U1, whereas du is not equal to U2 minus U1. It is a differential operator. That is a difference operator. So there is a difference between delta U and du. So this is the first equation we obtained. As well as we know that the enthalpy is given by U plus PV. This enthalpy is given by U plus PV. And this U is also specific energy. It is also specific enthalpy. This V is also specific volume. That is the enthalpy per unit mass, the intensity per unit mass, the volume per unit mass. So these are the specific properties. Now I want dH. dH will be equal to du plus d of PV, isn't it? Plus d of PV. So I will end up with du plus PdV plus PdP plus PdP. So it's dH. Now from this, what is du? du will be equal to dH minus PdV minus PdP. We have this as equation number 2. So from first law of thermodynamics, I ended with TdS equal to PdV plus du. As well as from the definition of enthalpy, I know H equal to U plus PV. I have ended up with the value of du. Now substitute 2 in 1. Now substitute 2 in 1, we get. So TdS will be equal to PdV plus dH minus PdV minus PdP. So we can see this as PdV and minus PdV terms will get cancelled. So we will end up with TdS equal to dH minus PdP. So we give this is equation number 3. I hope I am not fast. We have taken from first law of thermodynamics and enthalpy definition, and a substitutable value of du, we ended with the third equation. Now the main aim for me is to find the entropy change, that is S2 minus S1. So let us take from 1. From 1, what is ds? Integration by temperature. So it will be PdV by T plus du by T. So from 1, I am doing the integration by temperature. What is du? U is nothing but MCV T. So du will be equal to MCV dt. MCV dt. So here we are not considering capital U, we are considering only small u, which means the mass is unity. The mass is unity. So du equal to Cv dt. So we can replace du with what? Cv dt. Yes, Cv dt by t plus P by t of dV. P by t of dV. I have written this term as the first term and this term as the second term. Both the same. Now, what is the ideal gas equation? PV equal to mRT. Or P into small v equal to what? RT. What this means? Specific volume. Volume occupied by unit mass. So from this, what is P by T? P by T will be equal to R by V. So substitute for this P by T as what? R by V. So it is Cv into dt by T plus R by V into dV. ds equal to. Now we have a similar operator terms dt by t and dv by v, so we can integrate. So integrating the entire equation, when I want to integrate ds, it becomes s to the limits of 1 to 2. Cv is a constant. When I am going to integrate 1 by t, it becomes ln t to the limits of 1 to 2, isn't it? Plus r is also a constant. When I am going to integrate 1 by v, it becomes ln v, ln small v, 1 to 2. Okay, so it is s2 minus s1. Applying the upper limit minus lower limit equal to Cv into ln of T2 minus ln of T1 plus R into ln of V2 minus ln of V1. So it is nothing but Cv into ln of T2 by T1 plus R into ln of V2 by V1, because you know that log A minus log B will be equal to log A by B. So based on that we derive this formula. So we finally end up with the change in entropy S2 minus S1 is given by Cv into ln of T2 by T1 plus R into ln of V2 by V1 for unit mass of the gas considered. So this is the final formula what we derive for the change in entropy from 1. Now there is a question for me, whether this entropy change can be applied to a constant pressure process or a constant volume process or an isothermal process or adiabatic process or polytropic process. Which process we can apply this equation? For which process we can apply this equation? What is the answer? Arun, what is the answer? For which process we can apply this equation?
So for all the processes we can apply.
Yeah, this equation can be applied for any process because it is not derived on a particular process. It is derived from the first law of thermodynamics. So this equation is generous in nature or it is general in nature. It can be applicable for any process. It can be even applicable by a open flow system or it can be applied by a closed flow system. So this formula is more general in nature. So that is some doubts will come. So you should be very clear with that. Now let us move to the third equation. We will derive another formula for the entropy change. Let it be here. So let us take this equation from 3 TdS equal to dH minus V into dP. I want only the entropy change, so divided by T, it is dH by T minus V by T of dP. What is dH? It is H equal to mCp dt. Small h equal to Cp dt. Isn't it? Small h equal to Cp dt. So it is Cp dt by T minus V by T of dP. For the second term, we have to go with the help of ideal gas equation. PV equal to mRT. So P into small v equal to what? RT. So from this, what is V by T? It is nothing but R by T. Why we want in terms of this one? Then only I can integrate. So for V by T, I can replace with what? R by P. So it is Cp into dt by T minus R by P into dP. So what is the left side? ds. Now the terms are okay. Here also we have dt by T and dP by T. So we can integrate. So integrating on the entire thing, it will become what? S2 minus S1. I hope you can understand. Equal to Cp into ln of T2 by T1. Because it becomes ln T, so the upper limit minus lower limit, then we can make this one. Minus R into ln of T2 by T1. Okay, so this is the second formula for the change in entropy. It can be applied for any process. It is independent of the process. And what is the relationship between Cp, Cv and R? What is the relationship between Cp, Cv and R? Cp minus Cv equal to R. This is the relationship. So let us have this is equation number as 4 and this is equation number as 5. Now for R, you substitute what? Cp minus Cv. Okay, substituting for R in 5. Substituting for R in 5. So I will end up with another formula. S2 minus S1 will be equal to Cp into ln of T2 by T1 minus Cp into ln of P2 by P1 plus minus of minus will become what? Plus Cv into ln of P2 by P1. I hope I am not lost. Okay, for this R, I have replaced with one like this, Cp minus Cv. So into ln of P2 by P1. So the first term will be Cp into ln of P2 by P1. The second term will become minus of minuses plus Cv into ln of P2 by P1. Now we can combine these two terms and I can write as Cp into ln of P2 by P1 plus Cv into ln of P2 by P1. So this is nothing but what? S2 minus S1. How I got this relationship? Once again from the ideal gas equation. Ideal gas equation. How I will make these two terms into one term? That is from ideal gas equation. What is ideal gas equation? PV equal to what? MRT. So it is P into small v equal to what? RT. I want what? T by P. So it will become T by P will be equal to V by R. T by T will be equal to V by R. So T2 by P2 will become V2 by R. Similarly, because same gas only is expanding, there is no need of putting R on R2 because it is the same gas. So T1 by P1 will become what? V1 by R. So when I am going to take T2 by P2, divided by T2 by T1, divided by P2 by P1, I will end up with what? V2 by P1. So this equation will be S2 minus S1 equal to Cp into ln of V2 by V1 plus Cv into ln of V2 by P1. I hope we can understand this process. From these two terms, we can make these two terms into one term. Cp ln of T2 by T1 minus Cp ln of P2 by P1 as Cp into ln of V2 by V1. Based on this ideal gas equation, PV equal to RT. From this we can find what is the value of T2 by T1 and P2 by V1. Finally we will end up with the V2 by V1. So for this section gives an idea about the ideal gas equation in terms of mass basis, modal basis, and we come to know about the Avogadro's law and the application of Avogadro's law to obtain the value of R bar. Then we got the value of R for different gases. Then we also, from the first of thermodynamics and the definition of enthalpy, we derived three formulas for the change in entropy. In the next session, let us discuss about this partial law of Dalton's law of partial process, Avogadro's law of partial volumes, and how to find the equivalent gas constant, equivalent enthalpy, entropy, and other properties related to the gases mixtures. So with this section, we are ending up for the individual gases. In the next session, we will continue with the mixture of gases. Thank you.